Alright, so we start the differential equations, and then we are using Peter's note. So we're going through this, and then we'll also add Dawkins to that. Okay, then I think we will be fine. So make sure if you are there or you watch the video, you would make sure that you use those PDFs as your learning materials. Okay, all right. So there is a differential equation that we are going to do. All right, so the differential equation that we are going to do, we will need to study Laplace transforms, right? So with Laplace transforms, then we'll move on. Okay, so this is the lecturers, Dr. Peter Mwakunjerinchi. All right, so recommended textbook, elementary differential equations. Okay, all right, so this is a set of series of lectures notes that we are going to go through, right? So what is Laplace? So Laplace transform is a name after a French mathematician, and then his name is given like that. All right, so Laplace transform is most useful for solving linear constant coefficient ODEs. All right, so you want to solve ODEs that have constant coefficient. Okay, and when the inhomogeneous term or its derivative is discontinuous. Okay, so the main reason why you would want to use Laplace is to kind of solve this kind of equation. So let's say you have A, all right, let's say Y, let me use a second order, prime plus B Y prime, all right, then you have a C plus a C Y, right, equal to sum f of x. So equal to sum f of x. So you would want to solve this using Laplace approach. Okay, you want to solve this if provided the constant coefficients. So these are the constants A, B, C are the constant coefficients, and then these ODEs. Okay, ordinary differential equation. This is not a partial differential equation, ordinary differential equation, because remember, for ordinary differential equation there is one independent variable. Okay, so one independent variable, and then there is another one dependent variable. So you see that y is depending on x. Okay, so that makes it ODE, right? So there is only one. This is the independent variable, right? So there is only one independent variable. There is only one independent variable. So that makes this equation an ODE, all right? So when the inhomogeneous term, so remember that if this whole thing, when it's equal to 0, it is homogeneous. So this is the part that is making it inhomogeneous. Okay, so if this term, all right, if this term is discontinuous, right, it is not a function that is differentiable. It's not a function that is like continuous. Okay, it has some discontinuity, right? So you would want to assume this can be a step function. Okay, it can be a step function, maybe f of x. F of x can be a function. F of x can be a function. Let's say, let's take this. It can be this function that is off, right, when let's say when x is less than 1. Okay, then it becomes on. All right, it becomes on when x is let's say picks a value of 1 when x is greater or equal to, let's say, 1. Okay, so you may look at this and then there's some kind of discontinuity, or it doesn't look continuous, because this is how f of s has been defined. Then you cannot easily go ahead and then use the normal techniques that we know in solving differential equations, okay, higher powers. So you would want to use Laplace transform. So the basic idea is that we wouldn't have used Laplace transforms if this function is fairly continuous. It can be differentiable everywhere. Then we wouldn't want to worry ourselves doing that. You can use the various methods that are available. Method of variation is there. All right. You can use a method of undetermined coefficients. Okay. All those methods are there. So you could even go ahead and use those methods to solve that. But it happens that the inhomogeneous part at times it becomes discontinuous function, and you would have to adapt another technique, and that is Laplace transforms. Okay, so that is Laplace transforms. Laplace transforms. All right. So although ODEs with discontinuous inhomogeneous terms can also be solved by adapting already learned methods, we will see the Laplace transform. So even if this is discontinuous, there is some other methods that can solve, but it seems that if you have a constant coefficient, the Laplace works very better. Okay, so we will see that the Laplace transform, right, technique provides a simpler, more elegant solution. Okay, all right. So let's look at forward and inverse Laplace transform. Okay, so because we would take the Laplace and then after we want to bring it back. Okay, so you have the equation, you take the Laplace of all the expressions in the equation, and when you are done, you will bring back the Laplace, the inverse. You take the inverse and get your expressions. So what I'm trying to say is that you may have your equations in terms of y. Okay, let's say y prime plus 2y, let's say, equal to, let's say, e raised to the power x. Okay, you may have something like that. So the Laplace transform is saying, using that method means take the Laplace of everybody here. So you take the Laplace of everybody here. So that means you leave your equation now in terms of x's. Okay, it will be in terms of x's. So when you are done, everything will be in terms of x's. So you have to come back to y's. So you have to take the inverse. Okay, you have to take the inverse transform. So that's the reason why you need to know both the forward transform, that is transforming this into x's and then bringing back to y's. Okay, all right. So the main idea is to Laplace transform a differential equation with constant coefficients. So remember, this is the differential equation. We are solving differential equation with constant coefficients. So if the coefficients are non-constant, we wouldn't be using Laplace transform. Okay, so let's see that. So for ft into a simple algebraic equation for the Laplace function. Okay, so what we are saying is that if you have a function f of t, and you want to take the Laplace, remember, when you take the Laplace of this function, then we are saying that it is equal to capital. Immediately when you take the Laplace, it now turns to capital F of x. Okay, it's no longer small f of x, f of t. It becomes capital because when you take the Laplace, every t now is replaced by x. So you won't, after Laplace, you won't see the t, you'll be seeing x. Okay, and then what is f of x? Capital F of x. And we are saying that capital F of x is given like that, which is capital F of x. We are saying that is giving us the integral. All right, so capital F of x is giving us the integral from 0 up to infinity. All right, e raised to the power minus xt. All right, then the function you want to find the Laplace, which is f of x. So you put f of x there and then do derivative respect to what? T. So this is how you take the Laplace. Alright, this is a forward Laplace. So it means that if you have any expression in the differential equation, you have to take the Laplace of each of them. Okay, alright, sure. So I think this is the introduction. We'll continue by looking at some Laplace of some particular functions. Okay, alright.